In this video, we are going to start part 2 of the 4th unit in Calculus 1 class, and we're just going to practice some more with inflection points and the second derivative. This first example asks us to sketch a curve with the following properties. Now, before I start drawing them, let's think about what's happening here. Our first derivative is negative, and our second derivative is negative for the domain for all x values that are less than -1. So with a negative first derivative, that means the function is decreasing. And for a negative second derivative, that means that it is concave down. So whatever sketch that we create has to be decreasing and concave down. For this one, the function is still decreasing. We've got a negative first derivative. The function is decreasing, but it is concave up at that point. So the behavior of this function is decreasing yet concave up, which is possible. Then we switch to an increasing function. And we know what happens when we switch from a decreasing to an increasing function. We also have, again, a second derivative that's positive, so we are going to be concave up at that point. Next, we continue on the increasing movement because our first derivative is positive. Our second derivative becomes negative, which means we are going to be concave down. And again, anytime that we switch from positive to negative or concave up to concave down, we experience what we call an inflection point. So there's an inflection point here, even though there may not be a maximum or a minimum point because of the first derivative. And then for this last component, with a positive first derivative and a positive second derivative, we are still increasing, and now we are concave up. So before I sketch, I think I'll identify all of these key points on our x-axis, -1, 2, 8, and 10, and I'll just lightly kind of indicate those break points, if you will, with some dotted lines emanating from the x-axis. So those are the positions on the x-axis and the dotted lines associated with them. I try not to make those two stand out too much because they're really just guides for the behavior of this function. They don't really have any function values. So when I'm sketching, it helps me kind of see the behavior of the function a little bit better, but it's definitely not part of the original graph. So let's think about this. For the x values that are less than -1, so over here on the far left-hand side, we have to have a decreasing function that's concave down. Now, I can just pick some arbitrary point of the graph to draw that, but I'm going to make sure that it's up pretty high here because I know the function is decreasing. So to show a function that's decreasing and concave down, I'm going to make this sort of sketch. The second derivative does change from concave down to concave up, so this is a point of inflection, but the function is still decreasing. It's still decreasing, so the function is dropping, but it now has to be concave up, so that it's kind of turning upward like this. So I will note that there's an inflection point here. We change from concave down to concave up. The function is decreasing the entire way. But then at an x value of 1, we change from a decreasing function to an increasing function while still retaining the concavity that is pointing upward. Now here again, when we change from a decreasing to an increasing graph, we hit a low point in the function, and I'll make that one stand out here. We'll note that as a critical point because the first derivative is equal to 0. And it's a minimum in this case, since we change from a decreasing to an increasing function. At x equals 8, the graph continues to increase, but now the concavity changes. So we encounter another inflection point, and the graph is going to sort of turn to be concave down. Now again, it's still increasing, it's still rising against the x-axis, but it's turning downward. And then lastly, the function continues to increase, but then switches again to be concave up. So there's yet again another inflection point. So So again, recall that an inflection point identifies where the concavity changes. It doesn't necessarily mean that our second derivative is equal to 0 or doesn't exist. It just means that our concavity changes. For our critical points, however, that does indicate that the first derivative is either equal to 0 or does not exist. And I'd be willing to bet, if I had the function in front of me, that this would compute out to be a critical point. But we just don't know that for sure just yet because there was no mention of telling us exactly what the derivative value was at precisely 10. We know what it was surrounding 10, but not at 10 specifically. But if I had to guess, the derivative at that point is probably 0. Now, with your sketch, it doesn't have to match mine precisely, but as long as your sketch does meet all of the criteria, then I would be happy. And if you're not sure, please let me know. We can chat about your work. Now for these next two examples, we're being asked to sketch the functions by identifying zeros, critical points, and inflection points. And we should also consider the function behavior according to the function's first and second derivatives. So essentially, this is a no calculator question. I would like for you to generate the function at hand without the use of a calculator. Now, in the event that the math gets to be a bit challenging, maybe we could use a simple calculator to compute the arithmetic, but I don't want you to benefit from a graphing calculator to see what this looks like. I want you to use your analysis of derivatives only. So, as with most of our problems, we should start with the first derivative. And you really have a challenge in front of you here. The question that I would ask myself when starting this problem is, do I feel that it'd be worth it to FOIL or distribute these groups of binomials together? Now I know I can't distribute this 2 in, that's a no-no, but if I write x minus 2 times x minus 2 times x plus 2, I could then FOIL or multiply or distribute those three binomials together and get a single polynomial as a result. That may make it easier to work with the first derivative and the second derivative. However, we could find the derivative of this function by using the product rule as well. Now, I've practiced enough of these that I think I'm comfortable enough with the product rule. And I'm going to treat 27 as a coefficient, so I'm just going to toss it out front right off the bat so that I can ignore it. But then I'm going to treat this function as the first product or first element of the product, and then this function as the second. We'll also end up using a bit of the chain rule here as well because we have an inner function and an outer function too. But again, I think it'll be worth it to calculate the derivative in this way. So I'm going to do that now, and I would suggest that you find a method that's comfortable to you and pause the video and resume playback in a moment to check your work. And so that proved to be a pretty fun exercise in algebra, I would say. I had to use the product and chain rule to find the derivative first. So I took the derivative of the outside of this expression, kept the inside alone, and multiplied by the derivative of the inside. So that completes the derivative of this first function, and that derivative of the first function was multiplied by the second function untouched. To that we added the first function untouched times the derivative of the second function, which ended up being 1. Then I used some algebra from there. This exponent of 1 and this product of 1 essentially disappeared. So I distributed in my 2 to make this 2x minus 4. Multiply that by x plus 2, and we ended up with 2x squared minus 8 after FOILing. On the right side over here, x minus 2 squared required x minus 2 to be multiplied by itself. When FOILed, that generated x squared minus 4x plus 4. I dropped the parentheses and combined like terms and ended up with this expression and found that it was factorable. So 3x times x gives me 3x squared. 2 times 2 gives me 4. And by placing a negative sign here, the outside product of negative 6x when combined with the inside product of positive 2 brings me back to negative 4x. So what this tells me is that the first derivative is equal to 0 when x is equal to negative 2/3 and when x is equal to positive 2. These are our critical points. Now here's where a basic calculator would be helpful, because if I evaluate the original function, not the derivative, but the original function at these two critical points, then that's actually going to give me a position of the a position on the graph where our derivative is equal to 0. And when I do evaluate the original function at negative 2/3, I get a result of 256. And when I evaluate the original function at positive 2, I end up with 0. That one I didn't need the calculator for because of this 0 right here. So when I'm thinking of my graph, let's see if I scale this as -1, -2, -3. Well, what I do know is that there's a first derivative that equals 0 at negative 2/3, 256. So I don't know what my y scale is going to be, but I'm going to say that that point here and then this point's right here. We're at a flat spot here and a flat spot there. So that's the analysis that I can do with the first derivative, at least for right now. Let's consider the second derivative. Now, we've gone through the trouble of making a nice first derivative equation, so computing the second derivative can be based off of it rather than trying to worry about computing the second derivative off of this whole mess back here. Now that we are simplifying our expressions, it makes this next step a little bit easier. So here again we've got a coefficient 27 that I'm just going to push out to the front, and now for the derivative I need the derivative of the first function times the second, so that would be 3 times x minus 2 plus the first function 3x plus 2 times the derivative of the second, which is 1. Now that executes our product rule, and from here we can simplify. We've got 27 times 3x minus 6 plus 3x plus 2. I'm using square brackets while I have lots of parentheses on the inside, but now that I don't have many parentheses, I think I'll switch back to parentheses. And now we've got 27. The 3x's cancel. Sorry, they don't cancel, they combine to make 6x. And the negative 6 minus 2, I'm sorry, negative 6 plus 2 ends up being minus 4. And now if I distribute in, well, actually, I don't think that's necessary. I don't need to distribute in because what I would like to know is when the second derivative is equal to 0. That'll help me identify a potential inflection point. Well, that occurs when x is equal to negative 4 over 6 or negative 2/3. Sorry, not negative 4 over 6, but positive 4 over 6. If I set this factor equal to 0, I get 4 over 6 or 2/3. Now I don't know that that's an inflection point just yet. Just because the second derivative is equal to 0, I don't really know if that's an inflection point. So what I'll do is just make a quick number line here, mark 2/3, and I'm going to pick a spot to the left of 2/3, and then I'll pick a spot to the right of 2/3 and evaluate it in our second derivative. Well, I think two numbers that would work here are 0 and 1, and I'm looking at this form of the derivative. So I need 27 times 6 times 0, whoops, 6 times 0 minus 4, and that's a positive number times a positive number, so I know I'm going to have a positive second derivative here. In this example, I've got 27 times 6 times 1 minus 4. Gosh darn it, I keep making many little mistakes here. 6 times 0 is 0 minus 4. That's a negative number. And so therefore we end up with a negative result. The graph will be concave down in this region. But then in this example, we have a positive and another positive result, which will produce a positive portion to this domain. Our second derivative being positive, we see a transition from negative to positive, so yes, we do have an inflection point. So because of this test, we can say that there's an inflection point at x equals positive 2/3. And if I use a basic calculator to evaluate 2/3 in the original function, I end up with a coordinate 2/3, comma 128. So at 2/3 on our x-axis, we have a y value of 128. Let's see, that should be about halfway up from where 256 was placed, so I'll put a dot right here. That's an inflection point. And I think we've got a pretty good idea of what's going to happen in this graph, but just to bring everything home and to connect our first derivative test into this situation, I'm going to create a number line back here and investigate our first derivative. So we had a 0 at negative 2/3 and a 0 again at positive 2. And with a bit of mental math, we can kind of predict what's happening here. When we pick an x value less than negative 2/3, say negative 1, well, that's going to give me a positive number. 3 times negative 1 is negative 3 plus 2. That's a negative result. And then another negative number, minus 2. That ends up being a negative result. So we now have positive times negative times negative. The results in this region are positive. So our first derivative test indicates that these are all positive and therefore increasing. In between negative 2/3 and 2, we might pick the number 0. Well, here again we've got a positive result for 27. 3 times 0 is 0 plus 2. That means that group becomes a positive result, and 0 minus 2 is negative. So in this range, our calculated results will all be negative. And if we pick a number bigger than 2, well, positive 27. 3 times 2 is 6 plus 2. Well, that's a positive number. And then a number bigger than 2 minus 2 returns a positive number as well. So anything in that group will be positive as well. So the function's increasing, decreasing, and increasing again. The function is concave down and then concave up on these ranges. And now if we put all of that together, we can, I think, sketch a pretty accurate graph. Oh, and one more thing I forgot to point out back here. Since this was in factored form, we can easily find the zeros of the original function, where the function will equal 0. Well, that occurs at positive 2 and negative 2. So those are data points that we can plot as well. We already knew about this, but now we know about this point as well at x equals negative 2. So we've got all these data points and the behavior of the function to consider as well. To the left of 2/3, the function is increasing, and it has to increase through this data point and be concave down. I know that it's concave down because I'm considering a number that's less than negative 2/3. Well, that's way over here on this number line, so we're still concave down. All the way up until this position right here, we're going to remain concave down, but the function changes to a decreasing function at an x value of negative 2/3. So it's decreasing, concave down. The concavity switches at positive 2/3 to become concave up, which is a good thing because we have this low point, this 0, at this position on the x-axis, and it remains concave up for the rest of the behavior of the function, and the function is now increasing at positive 2. So it can be a bit daunting to incorporate both the first and the second derivative tests simultaneously. In the next video, or I'm sorry, in the next example, I think I will try to align those test points a little bit more clearly and perhaps emphasize them on the graph.